So, target 2 says I can solve trigonometric equations over a given interval. So that's different than the last notes where it was find all solutions. Now, you might think that this makes it easier, and in some cases it does make it easier. In some cases, you'll see that it's a little more challenging. The interval for these problems, for today's, are always 0 to 2 pi, so the unit circle. If you notice there's a bracket on 0 and a parenthesis on 2 pi, it's because those are coterminal. And so if you were at that location, 0 is what you would say, and you would not say 2 pi. So if you were at 0 radians, you would just say 0. You don't say 0 or 2 pi, and 2 pi would be wrong. So unit circle values only, which makes a problem like number 1 easier than what you've been doing. So let's just go ahead and do this one. So they're asking when tangent equals -1. If you don't feel the need to draw a unit circle, you don't have to bother. Tangent sometimes can be a little bit tricky, but 1 and -1 are the easiest two numbers. Tangent's negative in these two quadrants. And so remember that tangent values, the other one is across, and so they come in pairs, unless you're talking about, let me think. I mean, when tangent's 0 undefined, I guess it's across 2. So they usually come in pairs. 3 pi over 4, 7 pi over 4. Now, I'm not going to do the thing where I do the combining because I don't need all the coterminal angles. So that's it for this problem. So I started off with a fairly easy one. And it would be the same if it was a sine or a cosine problem. Don't write the ends. Don't write one end as an integer. Just list them. That is it. That's a pretty straightforward problem, right?
Yes.
Okay. The next problem, I have one where we haven't talked about what to do in this situation. So I'm kind of accomplishing two things at once here. I'm giving you an example problem that, is, this type of problem, but also something unusual is happening here. And this could happen in an interval from 0 to 2 pi, or a calculator problem, which we'll do in the next notes, or in a find all solutions problem. Okay, you need to know what to do when you have a 2x and an x. If everything's a 2x, you leave it all 2x's. If everything's 3x's, you leave it all 3x's. But if you have a 2x and an x, you got to do something about this. You might also notice that in this problem and the one below it, you have cosine and sine. So that's a little bit weird. We can't get sine and cosine both alone. So we have some different issues here. So occasionally you have to use trig identities. Okay? You won't need to use all the ones you learned. So you might have to use the Pythagorean identities. I'm not going to write those down for you, but the Pythagorean identities are sine squared plus cosine squared equals 1, and the 1 plus tangent squared equals secant squared, and 1 plus cotangent squared equals cosecant squared. So you can write this down on the top of your paper. You'll need to know the Pythagorean identities. And in one of the homework problems from homework 1, my gosh. So one of the homework problems, you need the Pythagorean identity. The other two identities that you might have to use, there's only two other ones. You might have to use sine 2u equals 2 sine u cosine u. And that, you might have to re-study. Or cosine 2u equals cosine squared u minus sine squared u. The other ones you won't have to use, okay? I'm just telling you that. Maybe in a different problem, in a different class, you might have to use other ones. But for me, I'm not going to have you remember all of those. And usually the other ones don't end up in these problems anyways. And let me just say this again. I'm not doing this because I see a 2x. I'm doing this because I have a 2x and an x and they're different. That's the issue. If this wasn't here, I wouldn't do the step I'm about to do. Okay, if you look down here, I have a sine of 4x. That's fine because there's not a 4x and something else. It's just a 4x. And I don't have a rule for 4x anyways. So I take that sine 2x and I substitute it with sine x, or 2 sine x cosine x. That is a identity that says you could replace this with this. And what I accomplished is I made everything x's. Now, before we didn't really know what to do, but now that I have everything x's, maybe you recognize what I can do here. It wasn't not obvious at all at this stage, but now I look at this and I say, okay, I have two terms. This one's got a sine, this one's got a cosine, but this one's got a cosine too. And, I got this equals 0. And one of my methods is factoring. And this one's factorable, okay? I could do a greatest common factor. And if it wasn't factorable, then maybe I have to do something else. And if you're wondering, what would you do if you didn't have a method? Well, one method, and you could do this to check your answers, is you could graph this thing on the calculator and find out where it crosses, in this case, the x-axis, or you could maybe, on this problem, graph this and graph this to find out where they intersect. Of course, you would get decimal answers, not exact answers. Okay, so I'm going to GCF, and I'm going to take a 2 and a cosine out. I really think that the first step was the challenging step on this one, doing that substitution. So I substituted, I did GCF. We've done GCF before. I do zero product property. I get cosine alone. Here I'm dividing both sides by 2. I don't even bother writing it. This 2 doesn't really do anything. This is actually another zero product property. It's 2 times cosine equals 0. It's 2 things that multiply to 0. Well, 2 can't be 0, so cosine could be 0. So I could use zero product property again, or I could just divide by 2. It's the same either way. Here I add 1 to both sides. And I have cosine equals 0, or sine equals 1. And I think about the unit circle, and I say this point right here, cosine is 0, that's 0, 1. And this point right here is 0, negative 1. And so for my cosine part, one of the answers is pi over 2. And one of the answers is 3 pi over 2. Any questions about this so far? Now, I added something else that might happen here. When you go to solve this sine equals 1, it's not a no solution. There is a solution. It's just that we already have it, right? Sine is equal to 1 at this same place. So I'm not going to write pi over 2 again. These are the answers. These are the only answers. Again, I'm only doing on the unit circle. So this is it. Those are my answers. And the problem is over. Everybody happy with that one? Okay, so I do a trig identity, I do factoring, I do zero product property, I need to know about the unit circle, a lot of stuff you need to know there. If you could do the first step, I think that you can do it. Now 3 is, unlike any problem we've done, we have a cosine plus 1 and a sine. I can't do any substitution right now that I would find helpful. On the homework, on problem number 7, it was something like this. It was like cosine squared plus 1 and sine, I can't remember what it was, but those were squared. Now, if I have a sine squared, I can make it a 1 minus cosine squared, and everything would be cosines. If I have a cosine squared, I can make that a 1 minus sine squared, and everything would be sines. But neither one of those are squared. Okay? I cannot make a sine into a 1 minus cosine. Okay, we got to make sure we remember that. That only sine squared can replace with something, or cosine squared could replace with something with Pythagorean identities. So I am going to use the Pythagorean identities. I just can't do it right this second. Does anybody have a theory or a guess or any idea what I would do here? Moving everything to one side isn't going to help. adding, subtracting, and moving things around isn't going to help because I still have a cosine and a sine. I either got to make everything sines or everything cosines. Any ideas? Well, I want this to be a sine squared. There's two ways to make that a sine squared. I could do things to both sides. No one's got any ideas? Square both sides. That's what I'm going to do. Okay, square both sides. Now, the other option would be to multiply both sides by sine. But remember, I'm trying to make everything into cosines. So if I multiply both sides by sines, then I'll have a sine over here. And then this will become a sine squared, which will become 1 minus cosine squared. But now I still have a sine. I don't want that. So I'm going to square both sides. Is squaring both sides okay for equations? Is that legal?
Yeah.
It's legal. Is there anything I need to worry about? Like, should I put a positive or negative? Just square both sides and move on with your life and don't look back. Is that what you're saying? Okay, well, let's see what happens. All right, I'm going to square both sides. Now, I am going to square this, and, you know, you have to square this binomial. So make sure you don't think it's cosine squared plus 1. You got to do FOIL. It's cosine squared, and if you need to write it out the long way, you can. But I have to multiply a cosine times 1 and then do that twice. So it's 2 cosine theta plus 1. That's what that binomial would square to. Again, if you had to write cosine theta plus 1, cosine theta plus 1, and do FOIL, you know, that's what you should do. But you got to know that it's not just cosine plus 1. If this is missing, it's going to mess up the whole thing. And then that sine squared, remember that writing like this is just plain sine squared. I'm not even going to bother writing it down. My whole reason for writing this is to do a substitution. That's using a Pythagorean identity. Sine squared, which is what this is 1 minus cosine squared. Now I have all cosines in the problem. Okay, now I can get someplace. All right. So I'm going to get everything on one side because it looks like I need to factor. I have a cosine squared in the problem, and I also have a normal cosine that's not squared. That leads me to believe I'm going to need to factor. So I'm going to move both of these over and make this side 0. And I get 2 cosine squared theta plus 2 cosine theta. And that 1 just goes away. And, you know, that just happened. I mean, that's not something that always happens. But it happened in this problem. If that 1 was still there, I would need to do a different type of factoring, but this is another greatest common factor problem. So I GCF cosine, 2 cosine again. If you accidentally just take out cosine, it ends up working out fine. But, you know, we're doing greatest common factor, so you would take out the 2 as well. This kind of looks like the last problem, especially on this left side. So that 2, I just divide by 2 or ignore the 2, and I make that cosine equals 0. Here I move the 1 over. I get cosine equals -1. So you might say, okay, this doesn't seem too difficult. You know, I needed to substitute, you know, that's an identity that we're good at, so we squared both sides. But we haven't got really to the part that is the main issue here. So, you know, please pay attention to all of this because we haven't even talked about the main thing to be concerned about. And no one seemed to know about it. So we'll talk about it in a second. All right, cosine equals 0 at these same 2 spots. And cosine equals -1 at this spot. So cosine 0, when x is 0, that's here and here. And cosine's -1. Remember, cosine is just an x value, so I just go where x is -1 on the coordinate plane. Remember, these are the x and y axis. So I don't have to think about combining or anything like that. I just have these 3 locations, and I just write them all down. So I have, I have pi over 2. I have negative pi. What? Not negative pi. What am I saying? Sorry. Pi. I was thinking to myself that pi makes it negative 1. Pi and 3 pi over 2. I mean, negative pi would be the same location, but we're only listing answers from 0 to 2 pi. Okay. Everybody followed everything I did there? And you think those are the answers? We're going to check these answers because there's an issue here. So I'm going to check them one at a time. Okay? When I plug these in, I got to plug into the original, not the squared one. So I'm going to go cosine pi over 2 plus 1 equals sine pi over 2. You should write this down. You have to check this one. I haven't said why yet, but you have to check this one. All right. Cosine of pi over 2 is 0. You know, we just did this one, right? We know this is 0. And so that would be equal to 1. This point right here is 0, 1. So sine of pi over 2 is 1. So 1 equals 1. Checked. Okay, that sounds good. Let's check the next one. I have cosine pi plus 1 equals sine of pi. Cosine of pi is this point right here. This point is negative 1, 0. So that gives me negative 1. And sine of pi is 0. So I get 0 equals 0. You know, I checked these two. I should feel pretty good about this. But let's do this other one. This is this point down here. And cosine 3 pi over 2 is 0. Sine of 3 pi over 2 is negative 1. Uh-oh. I got 1 equals negative 1. So then obviously I should just scratch all this out and write IDK, right? Give up. Say I had no solution. This answer does not work. The other ones do. Anybody have a recollection of what that is called? You get this kind of thing sometimes when you square both sides. When you square both sides, you don't just say, I'm squaring both sides. That's a perfectly acceptable thing to do. And I don't have to worry about anything else. You do. You have to worry about this kind of thing happening. No one remembers what this is called? It starts with an E. Extraneous solutions. You get extraneous solutions sometimes when you square both sides. Squaring both sides, every time you do it, you got to say to yourself, I'm squaring both sides. There might be extraneous solutions. It's the same thing if you multiply both sides by something with a variable. That doesn't happen in this chapter too much, but sometimes that people might do that. If you multiply by something with a variable, like if you multiply both sides of an equation by x, there are problems where people do that. Maybe they're trying to get a common denominator or get rid of fractions or something like that. But when you square both sides, you might have extraneous solutions. Why does that happen? Okay, let's circle these, get rid of that one. Why does that happen? Well, let's just talk about squaring both sides, okay? So you can just watch this. So watch and learn. Don't write this down. Like if I have 8 equals 8, that's true. And if I square both sides, it's still true. We want true things to stay true. So that's great. If something's true, it's going to stay true. Same thing with if I have negative 5 equals negative 5. If I square both sides, I get 25 equals 25, still true. So true things stay true. That's really important when you're doing operations on both sides. You need true things to stay true. But what about if it said 8 equals negative 8? If I square both sides, I get 64 equals 64. Do you agree with that? So there's some untrue things that become true. That's the issue. Is that there might be two things that are not equal, that when you square them become equal. So all the true things stay true all the solutions are still solutions, but you might have things that look like solutions but are actually not. And it won't always literally be opposite numbers like this, because it might be two things on the same side, but it's because of opposites. So it won't literally always be like 1 and -1 or 8 and -8. It might be like 1 minus, it might be like 3 minus 3 equals 0 when you go to check it, but it's still because of opposites. So it's because of that rule. So this number does not make these equal, but if I square these two things, if I square them, they become 1 equals 1. And I did square both sides. And so it made this untrue thing look true. That's what exchange solutions is from. And, that doesn't happen on adding to both sides, subtracting both sides. But it does happen when you square both sides. So squaring both sides, that's one instance of needing to check. Multiplying by something with a variable, that's the other instance. Everybody follow all that? So I'm not telling you to check every single problem you do. But if you multiply both sides by like sine x, or multiply both sides by cosine x or tangent x, or if you square both sides, you have to check for exchange solutions. Okay. Next problem. Last one we're probably going to do today. Okay. If you fell asleep, wake back up for this one, because this one is unlike any of the problems that we've done, and it really is like a totally different thing that you kind of have to prepare for and know how this works. I have sine 4x equals root 2 over 2. Now, if this 4 wasn't there, this would be an easy problem. If that 4 wasn't there, I would just say pi over 4 and 3 pi over 4 done. Okay? And if you remember before, we would do the thing with the ends, and you might say, okay, well, then just take 4x, set it to equal pi over 4, divide by 4, and get pi over 16. And pi over 16 is one of the answers. Pi over 16 is one of the answers, but it's not that easy. Okay. So, draw a circle. Let's find where sine is root 2 over 2. It's at pi over 4 and 3 pi over 4. It really helps to understand why this one is going to require a different approach. If that 4 wasn't there, those are the answers, and it's over. Now that 4 is there, and if I did divide this by 4 and get pi over 16, that would be an answer. Pi over 16 times 4 is pi over 4, and sine of pi over 4 is root 2 over 2. And if I divide this one by 4, I get 3 pi over 16. That's an answer too. You follow me so far? And I want all the answers from 0 to 2 pi. Okay. Do you agree when I divide these by 4, they get smaller? Right? Pi over 4 becomes pi over 16. It's smaller. You follow me? Okay. But pi over 16 and 3 pi over 16 are not the only answers. There are other answers. There's more than 5 answers to this one. Does anybody have any explanation of where these other answers could possibly come from? Why there would be more? Why would there be more answers? I mean, these are the only answers from 0 to 2 pi. I divide them by 4, and they get smaller. Where would other answers come from? Okay, I'll tell you. Nobody knows. There are numbers that are bigger than 2 pi that if you divide them by 4 are now less than 2 pi. So, for instance, 9 pi over 4, that's not between 0 and 2 pi. But if I divide it by 4, it becomes 9 pi over 16. That is less than 2 pi. Does that make a little bit of sense? So there's numbers that are bigger than 2 pi that I don't have written down But when I divide it by 4, because I'm dividing every answer by 4, it's now going to be less. So let me show you graphically. You don't have to write this down. You can just watch this. This is not our method of doing this problem. But this is what sine x looks like. Sine of 4x. That one is a horizontal shrink. And so it looks, I hope I could do this right. No, I'm doing it wrong already. Sine 4x looks like that. So when I go to say, when is this root 2 over 2? The blue one would have 2 answers, but this red one has 8 answers. There's 8 answers to this problem. Okay, so you might not know what they are, but there's 8 of them. So there's 8 answers that I'm looking for. And it's because sine 4x, looks like this. And like I said, when you divide things by 4, they become smaller. Okay, so let me say one last thing before I actually show you how to do the problem. If there's a 4 there, there's 4 times as many answers as there would have been. Okay, and it doesn't mean there's always 8. Okay, so if this had a positive or negative, there would have been 4 answers, and then that 4 would multiply by 4, and there'd be 16. If this was 0, that's an example. If this is 1, there'll only be 1 answer, and now that 4 would be 4 answers. So it's the number of answers there would have been times 4. So it helps to know how many answers there are. Okay, so how do you do the problem? So even though I'm not doing all solutions, I'm going to do the same thing I did with the ends. So this is just like the first notes. I'm saying 4x equals pi over 4 plus 2 pi n. If it was an all solutions problem, this is the way I would do it. And I'm not leaving this, obviously, because I don't want all the answers. I just want the answers between 0 and 2 pi. So I do the same thing I did in the other problems. And then I'm going to divide everything by 4, which, like we said before, is like multiplying by 1/4. So really nothing is different than the first notes on problems like this. Yet don't bother writing when n is an integer. N is an integer, but it's not our final answer. If it said find all solutions, this would be the answer we write on n as an integer. But remember, there's 8 answers. I need all 8 of them. And this is a list of all the answers. Okay? So it's nice that we have a list of all the answers, but we got to get it so that we only have the ones that are 0 to 2 pi. And like I said, you could see it here, why there's 8 of them. I talked about, there's numbers bigger than 2 pi. Then when you divide by 4, they're now less than 2 pi. Last thing before I tell you how to finish this problem. So I'm looking for answers 0 to 2 pi. Anything that's from 0 to 8 pi, if I divide by 4, is now from 0 to 2 pi. So really I have to find all the answers from 0 to 8 pi and then divide by 2. But I'm not literally doing it that way, but that's kind of a way of thinking about it, of why there's more answers. All right, so I wouldn't do this on other problems, but I do this on these problems to make it easier. I'm going to get a common denominator. So I am going to take these two fractions and say, okay, what's the common denominator between 16 and 2? The common denominator between 16 and 2 is 16. So I get a common denominator, and this is 8/16. I'm going to do that here too. And then I'm going to literally plug in numbers for n. So I make n equals 0, and I get pi over 16. We already knew pi over 16 is an answer. The good news about these 8 answers, I don't have to check any of them. Okay, they're all, if I do this right, they're all going to work. They can't be extraneous. It's not every problem can have extraneous answers. It's only certain problems that could have extraneous solutions. This one can't. We didn't square both sides or do anything unusual. So I make n equals 0, and I get this. Then I make n equal to 1. And when I plug 1 in, now that I got a common denominator, I could just say, well, this would be pi over 16 and 8 pi over 16. That's 9 pi over 16. If any of these fractions simplify, let's say you get 12 over 16, you have to simplify fractions, always. Okay, this one doesn't simplify. In this problem, none of them simplify, but there are some that they do simplify. So if you get any that simplify them. And then you could say, you know what, when I go to plug in 2, I know I'm just going to add 8 to the top. Okay, so I could just start adding 8 to the top and not really, plug in numbers, but I'm plugging in 3 now, and I get 25 over 16. The next one would be 33 pi over 16, but don't write that one. Okay, don't write that one. Why is 33 pi over 16 no good? It's too big because it's bigger than 2 pi. And the whole point of these problems is find all the answers between 0 and 2 pi. This is over 2 pi. So I stop on that one. Okay, then I do this one. And I make n equals 0. And I get 3 pi over 16. And then it's adding 8 to the top again. And I always check these to see if any of them can simplify. I don't have an example on this note where these fractions simplify. It does occasionally happen where you get like 24 over 16 or something. But I get this list. And it really helps to know before you start, this has 8 answers. Okay? Let me say this again. If that 4 wasn't there, these would be the 2 answers. It would be 2. If there's a 4 there, 4 times as many answers. That's how you would know how many answers there would be. And so there's 8 answers, and you just plug in n equals 0, n equals 1, n equals 2, n equals 3. And like I said, once you notice there's a pattern, you just follow the pattern. Any questions about this so far? Okay, last thing. This is important to me, and if you do it, I'll live with it, but please don't rearrange these, okay? When you get all these answers, don't put them in numerical order. Put them in the order you found them and just leave them, okay? Sometimes people rearrange them. They put them this one, then this one, then this one, then this one. They put them in numerical order. And that's fine if they're all correct. But what happens is some people do them wrong, and then they rearrange them. And it's really hard for me to figure out which ones are the right ones, which are the wrong ones when they're all rearranged. So don't rearrange them. As you get them, list them as you get them, and then just circle them in the order that you got them. Please don't rearrange them. It makes it harder for me, and there's no reason that you have to rearrange them. It would just be an extra step anyways. Okay.